To calculate the exact energy states of a single 9-atom molecule using classical physics software, you have to wait about an hour. A neural network can predict those exact same properties in 10 milliseconds. For decades, researchers have relied on density functional theory, or DFT, to simulate quantum chemistry. It accurately maps out electron distribution, but it carries a severe mathematical penalty. DFT's computation time scales to the cube of the number of electrons. If you double the size of the molecule, the simulation takes 8 times as long. This strict bottleneck makes simulating large, complex drug candidates practically impossible. Escaping this bottleneck requires moving away from simulating physics entirely. Instead, we must treat quantum mechanics as a statistical pattern matching problem, solvable with machine learning. Most deep learning models are structurally rigid. Convolutional neural networks, for example, assume data exists on a strict, predictable grid, like the pixels in an image, where every non-border pixel always has exactly 8 neighbors. Recurrent neural networks assume data arrives in a strict sequence, like tokens in a sentence, where one word naturally follows the previous word. Molecules do not fit into grids or sequences. They are irregular graphs. Atoms operate as nodes, and the covalent bonds connecting them act as edges. This creates a structural challenge called the variable neighbor problem. A carbon atom might share 4 bonds in a complex ring, while a neighboring hydrogen atom only shares 1. Standard neural networks cannot process inputs that change shape and size dynamically. Computer scientists have studied variable neighbor graphs for decades. Look at this photo. This is the Zachary Karate Club dataset, a classic social network problem. By treating these individuals as nodes and their social interactions as edges, algorithms can predict which of the 2 factions a member will join after a club schism. In 2017, researcher Justin Gilmer and his team adapted this graph logic to chemistry, developing the Message Passing Neural Network, or MPNN. They trained it on QM9, a dataset of 130,000 small organic molecules. To predict quantum properties accurately, the model had to absorb the actual spatial and chemical topology of the molecule, exactly as it exists in 3D space. To represent a graph's connections mathematically, we use an adjacency matrix. Here, a 4-node graph sits next to its 4x4 matrix. If 2 nodes share a bond, a 1 goes in the cell. But this matrix has a permutation flaw. Because nodes lack an inherent sequence, renumbering the atoms completely scrambles the matrix, even though the physical molecule hasn't changed. It also fails at scale. With thousands of atoms, entries grow to n squared. Since atoms only bond to a few neighbors, this massive tensor becomes mostly empty space, wasting memory on zeros. A neural network built for chemistry requires permutation invariance. No matter how you order the data going in, the network must compute the exact same physical result coming out. We solve this by replacing the matrix with an adjacency list. This diagram shows the matrix dissolving into a simple 2-column format that only logs the active edge connections between nodes. This format drops the computational complexity from n squared down to n edges. The network only spends compute power where actual chemical bonds exist. With the structure defined, we map the raw data onto it. The nodes store vectors describing the atom's identity, like carbon or oxygen, while the edges store vectors detailing the bond type and the physical distance between them. Securing a permutation-invariant, memory-efficient data structure is the mandatory prerequisite. Only then can the neural network actually begin to learn. The MPNN operates through 3 localized phases: message, aggregation, and update. Let's isolate a single atom to act as our target node, labeled V. This equation represents the message phase. We are calculating the message M flowing into node V at the current time step. Inside the function, the HW term extracts the hidden state, the chemical feature vector, of an immediate neighbor node. The EVW term extracts the data of the edge connecting them, factoring in the bond type and spatial distance. The summation symbol is how the network handles the variable neighbor problem. It gathers all incoming messages from every connected neighbor, regardless of whether there is 1 neighbor or 4. Summation is the preferred permutation invariant aggregator because it captures the total volume of local features without losing outliers. Once the messages are gathered, we move to the update equation. This shows the target node V receiving the final aggregated message M. The aggregated message is passed through a learned function, specifically a gated recurrent unit. The GRU takes the new neighbor data and overwrites the target node's previous hidden state. The atom now has a mathematical understanding of its immediate surroundings. The network iterates this entire three-step process k times. This is the network's depth. After 3 layers, our target atom has absorbed information from nodes 3 bonds away. Mathematically, this is matrix multiplication. Taking the adjacency matrix to the power of k equates to counting all possible walking paths of length k across the graph. The MPNN essentially creates a customized, localized neural network for every single atom, running them all simultaneously to build a holistic representation of the molecule. Purely localized message passing hits a limit. In a long, chain-like molecule, information struggles to propagate efficiently from one far end to the other. If you try to solve this by adding more processing layers, you encounter the dilution problem. Over successive iterations of gathering and averaging, the distinct chemical signals of individual nodes become washed out. Gilmer's team bypassed this by introducing a master node, also known as a global context vector. This schematic shows a central hub generating virtual edges connecting directly to every single atom. During every time step, every node reads from and writes to this global scratchpad simultaneously. This reduces the communication distance between any 2 atoms to exactly O of 1. Data from a fluorine atom on the left instantly informs a carbon atom on the right. The master node allows the model to process highly localized covalent bonds while simultaneously monitoring the electronic state of the entire molecule. After k steps of message passing, every atom contains a highly refined vector detailing its place in the molecule. The final step is the readout phase, which condenses the graph into an actual prediction. The network uses a set-to-set operation. It pools all the unordered node states, applies a linear projection, and compiles them into a single graph-level embedding. This readout layer outputs 13 distinct scalar values simultaneously. These map directly to the targets calculated by traditional physics simulators, like the zero-point vibrational energy or the HOMO-LUMO electron gap. This chart recreates Gilmer's empirical results on the QM9 dataset. The column labeled ENNS2S tracks the MPNN's performance against traditional baselines. The key metric is the error ratio. Dropping below 1.0 means the model surpasses the precision requirements set by the chemistry community. That threshold is chemical accuracy. The neural network is predicting the targets of a 1-hour density functional theory simulation so precisely that its margin of error matches the limits of a physical laboratory experiment. With sub-second chemical accuracy, researchers can screen millions of drug candidates and battery materials in the time it took to evaluate a handful. By utilizing relational inductive biases, designing an architecture that respects the mathematical reality of graphs, MPNNs prove that structural intelligence can reach the same conclusions as a physical simulation.